Hello and welcome to Foray. This is our astronomy foray, and we're going to talk about light and history today, as well as gravity and distance and relative and space-time later on. And the front page here actually deals with more or less the relative and space-time. This is All Hallows Eve, or at least the evening before All Hallows Eve, and I actually 38 years ago asked my wife to marry me on All Hallows Eve. So tomorrow evening will be our 38th anniversary for that proposal. We've actually been married for 36 years now, so I was a very lucky man then, still am. But anyway, if you take a look on the front page, this is dealing with relative and space-time, and we have Albert Einstein here, and he's got his famous clock, and what he's basically saying is if that you could hop into a rocket ship and leave your family here home on Earth, you would jump in that rocket ship and you would travel around look at your clock, and maybe 2 days later you can come back to the Earth, and let's say you were traveling very, very, very quickly. You jump off the rocket ship, and boy, they say that was a 3-hour trip, but that was amazing. And then you would look at your brothers and sisters and maybe your parents, and they would say, "What are you talking about? You were gone for 5 years." I said, "No, I was only gone for 3 hours. And I can prove it. Here's my clock." And well, we can prove it too. Look at everything around you. Look how old we are. Look how young you are. And that's basically what he was saying in this whole time continuum. So basically what's going on is we could take time normally is in a linear fashion, but if we could bend it, we can actually make the future really close to the present, where instead of having to travel this whole linear line all the way around, we could actually bend time so that they're right next to each other and jump through a wormhole and actually go to the past or go into the future very quickly, like jump into a box, come out later, and it's 40 years later. Here's another depiction of it where we actually have gravity bending the time warp, bending time. And if the bend is enough, we could actually create what's called a wormhole, and we can actually have time periods that are relatively close to each other when they're really supposed to be a long way, just by bending the time continuum. Okay, star color and temperature. What we have to do here is we have to assume that all characteristics are equal, that the distances are the same. Because if we start looking at big stars, they could be big because they are bright, they could be big because they are close. So we're going to actually make all other characteristics true. We're just going to look at color and temperature. Okay, so here are a bunch of stars. Here's Rigel, this is Betelgeuse, this is Algol, and very similar to the Sun size. And actually I don't remember which star is which, but this is a blue giant, this is a red giant, and this is the Sun. But one of the stars I think we're going to see here is Algol. And Algol is actually supposed to be the eye of Medusa. So it's actually in the Perseus constellation, where Perseus has already cut off the head of Medusa. And can't remember if it's the right eye or the left eye, but it's the biggest eye in Medusa's head, and you can Google that very easily. In fact, I can probably pull that up. Give me a second here. I can actually show you. Here is Perseus, and there is Algol, and is the eye of Medusa after Perseus has used the sword and the shield to not look at Medusa's head, but to cut off the head of Medusa, saving Andromeda, which makes Zeus real happy. Okay, so all stars being equal, the hotter the star, the brighter the star. The color of the star depends on its temperature. So the hotter temperature, which is usually higher energy given off, which actually creates shorter wavelength light, is going to be the blue color star, and the ultraviolet end. So we got ultraviolet, and you go into X-rays, and you go into gamma. So it's the high energy, low short wavelength part of the electromagnetic spectrum. Cooler stars, lower energy, longer wavelength light, they're going to be the red stars like this, and they're going to be on the infrared side, even going towards radio waves. So they're going to be brighter in other wavelengths, not so much the wavelengths we see. But the blue stars are going to be hot, and the red stars are going to be relatively cool. And then we look at this yellow-orange star down here, the Sun, or medium temperatured. And then they actually have some planets here too that would not be the Earth. Maybe, can't even be Jupiter. I'm not sure what that is. Like I said, I don't remember where I got this picture. But blue stars are hot, red stars are cool, and stars, other colors like our sun, we're somewhere in the middle temperature. So, star color, which are called the spectral classification, oh, be a fine girl, kiss me. How astronomers came up with these letters, I'm not sure, but basically we have O stars and B stars and A stars and F and G and K and M. And how are you going to remember this order? Oh, be a fine girl, kiss me. You can also say guy, but there's the O, B, A, F, G, K, M, O, B, A, F, G, K, M. And it actually works out that there are different levels of O stars and B stars and A stars and F stars, and we'll talk more about that later on. But basically, stars that are O are the incredibly hot bluer colored stars, and the stars that are called M are the relatively cool red colored stars. And if we get, we don't really get stars that are hotter than 100,000 degrees Fahrenheit, and we can't see stars that are cooler than 3,000 degrees Fahrenheit, because if they get cooler than that, they stop producing the visible light. You can still see them if you look for IR light, but you can't see it visibly. And here's another classification showing the O, B, A, F, G, K, M stars, and you can see blue at this end and red at this end, and the sun being that orangish, yellowish star that's sort of in between. Okay, so we have star classification. Here's another depiction of it, showing O, B, A, F, G, K, M with orange stars and not so blue stars in the middle, red at one end, blue at the other end. These are the Pleiades. These are the hot seven sisters. These are very hot blue stars, very young stars going through and burning their fuel very quickly. And I said burn, they're actually using fusion very quickly. And this is a star cluster. You can start to see the nebulous gas in between that was actually pulled together to make these stars. So this is still a very young constellation. Where do you find the Pleiades? Pleiades are really close to Taurus, the bull. They're actually part of the body of Taurus. Taurus has a very small body, but this is the seven sisters, the Pleiades. This is the Hyades, and the next star we're going to talk about is Aldebaran, this red giant inside Taurus, looking at Orion, and its red giant called Betelgeuse, and its blue giant called Rigel. But this is Aldebaran. Aldebaran towards the sun, you can see the size difference, and if we had Aldebaran as being our sun, we'd have a totally different looking Earth for sure. Okay, and again, Pleiades and a red giant. There's our sun, kind of an orangish, yellowish star. We'll talk much more about it later on in terms of the corona, prominence, sunspots, solar flares, coronal mass ejections, all that kind of cool stuff going on stars. So relative size, the sun and Rigel. We have Betelgeuse. We have the sun and Rigel and Betelgeuse if we actually look at density, and this is the sun, Rigel, and Betelgeuse if we look at their size. So our sun is fairly dense, but it's not as dense as this star. You can see the difference. Actually, we shrink Rigel even more to make it the same density, and then Betelgeuse, a huge monster star, we'd have to shrink it very much to have the same density. So size is the same scale here, and this one's density. What would we have to do to the stars to make them the same density as the sun? Okay, and here's Orion. There's Betelgeuse showing that nice beautiful red color, and there's Rigel down there with a nice beautiful color. Long exposure film, lots of other stars in the background. Spectrum and spectral lines, we have what are called continuous spectrum. This is when we actually see starlight without anything in between, and it actually makes a continuous band of color, long wavelength red. And if you think about Roy G. Biv, red into orange, into yellow, into green, into blue, into indigo, into violet, and that is the continuous spectrum. But we actually have ones that actually show spectral lines also, and these spectral lines are really important because they can help us with the chemical identification of stars. They come in two kinds. We have what's called absorption line spectra. So there's the continuous spectra with colors that have been absorbed and taken out. And we also have what are called emission lines, where basically we have the continuous spectrum and they just show us the colors that were taken out. And the reason we get these is a couple of different ways. They're caused by atoms of gas absorption or the emission of photons, the light particles. And the way it actually works is a continuous spectrum comes from a star absorption line. Actually, when starlight actually passes through another gas, like maybe its upper atmosphere or a nebula that's in between, and then we have emission lines with the same gas against a very cold, dark background. And the way it works is continuous spectrum is when we can look at the light from the star independently. If we look at the light from a hot gas, not so much a star, then we get what are called emission line spectra. And if we actually look at a star through a cooler gas like nebula, we get what's called absorption line spectra. But either way, we can actually get the lines for particular chemicals for nebula, or we can get them from stars, which can actually tell us the chemical background of stars. Looking at chemicals, you can see these beautiful colors. You can see a couple of colors for hydrogen, more colors for helium, less for lithium. You can see what's called the sodium doublet, two yellow lines right there. But if you take a look really quickly, you can see that these are all different. It's like fingerprints for the chemical elements in the periodic table. So what that allows us to do is to actually look at stars and actually see the chemicals that are made up. And we can see whether it's hydrogen, helium, lithium, oxygen, carbon, nitrogen, or neon. These are the most common elements up in the stellar composition. So when looking at O stars, and remember O be a fine girl, kiss me, looking at O stars, the bluer color, the O color, that's because the colors are brighter in the blue range because they're much hotter. The cooler colors are not really showing up because the brighter, hotter colors are there. And if you look at the colors, the shift goes more towards the red. And then eventually we get to the M stars. The purple colors, the blue colors are very dim, and we have the red colors and the orange colors very bright. This is how we get this spectral color classification, and we'll talk about this again when we talk about HR diagrams. So looking at the spectra of stars, or through a spectroscope or a spectrograph, we'll be looking through a spectrograph. Spectrographs actually give you the numbers for these particular wavelengths, whether it be long wavelength red light, or a shorter wavelength violet, or in between all the other colors of the rainbow. So what does this analysis tells us? It tells us the elements that we can identify in the star. It tells us where these elements are located, whether they're actually in the star or the upper atmosphere, or if they're in a nebula in between. It can be the star itself, it can be the upper atmosphere of the star, it can be a gas cloud that's directly between you and the star, or it could be a gas cloud that has no stars behind it, so we're actually looking at the gas cloud itself. So this is cloud emission, this is a hydrogen emission, and this is part of the large Magellanic Cloud, which is visible in the southern hemisphere, not so much for the northern hemisphere, and beautiful red colors of the hydrogen variety. And this is an oxygen emission, beautiful green colors, and this is in Triangulum, that constellation we found in October. And this is a nebula. It's called the National Galactic Catalog number 604, and we'll talk more about those later on too. And that's where we're stopping for this one. So that's a 13 and a half minute video, and thanks for stopping by. That's 4A Astronomy. Adios, and happy Halloween. See you tomorrow, at least first period.